Thank you very much, Tim. So I've titled the talk that I'm going to start out with implicit solvation models. This is what I'm going to try to cover today. And depending on how much time I have tonight and tomorrow morning, I'm going to give you a more or less deep introduction into classical DFT, where I know a lot less about it, but I think it's a topic we all should learn something about because these methods are intrinsically linked to each other. So in the part one today, I'm really going to talk about implicit solvation models, and several of the talks we've heard throughout the tutorial have already touched on using some of them and their need for them, but let me make sure we're going through some of the background to make sure we have everybody on board in order to really build models we can improve throughout this program. So we have electrochemical and catalytic processes at solid-liquid interfaces, and they're essentially controlled by solvent effects. Solvents, in most of the studies we're going to discuss in this workshop, are probably water, but there are many other solvents around that are used in technological processes like CO2, and there are also solvents around that are interesting for exoplanets and other things. NASA's interested in Titan and the chemistry happening there. Those are methane solvents there and stuff like this, very different. So we should keep an open eye on that, and I'm going to say a little bit at the end of the talk about the accuracy of these models for different types of solvents. We can, of course, in principle, do always explicit solvent models. So in other words, we have the models, we have density functional or other quantum mechanical methods where we just keep the solvents explicitly in the problem. And that is good because in other words, we have a benchmark of accuracy against which to compare. But these are very expensive. They may have their own accuracy issues in some cases. And the main problem is, because we're dealing with liquids, we have to do the thermodynamic sampling. And so effectively sampling those, we've just heard in the previous talk, is a whole nother ballgame. And that's why we're really trying to get rid of explicit solvent models wherever possible and implement implicit solvent models that are computationally much more efficient. The main idea, and that's the one thing you should definitely get away from this talk, and I hope I'm going to get a couple more messages across, is that we're trying to replace our H2O molecules with a smeared out mess, with a smeared out beautiful homogeneous background that is called the continuous polarizable medium. That looks much more simple. All the high fluctuation in space and time are all smeared out, and we get something much simpler, very efficient to implement, and for some cases sufficiently accurate. Obviously, you can already tell if I smear all this stuff out, I will lose a lot of resolution and accuracy in various ways, and I'll show you later on what the accuracy actually is of these various methods. So we want to efficiently simulate electrochemical interfaces. So we got to have electrical fields in there, we got to have the continuous polarizable medium in there. Electrochemical interfaces isn't just pure water, there's always ion in solutions, we got to deal with those as well. The models that are built based on those kind of ideas are VASP-SOL, JDFTX, SALSA, and CANDLE, which are parts of JDFTX. And then there's a whole zoo of solvation models, which I don't list here. I mention a few later on, which are in quantum chemistry methods. Gaussian has a whole bunch of those implemented, etc. And if you have specific questions, I'm happy to talk, but I'm going to focus on a subset of them today. So let's first look at an electrochemical interface in order to define the regions that actually are there and the ones we're really interested in. You've got to have some sort of an electrode. It's typically a metal, could be a doped semiconductor, and that's going to be our reservoir of atoms, definitely our reservoir of electrons. And so this is typically described in these methods by explicit density functional theory or some quantum chemistry method. Out here on the right, we have our water, and this is a part where not much is happening. We're far away from the electrode, and so in that case, we're going to describe that by our implicit solvation model, and I'm going to show you later that we obtain the Poisson-Boltzmann equation there. That's our electrolyte region out here. And then the interesting part, where almost everything is happening, and which is the focus of this workshop, where all the temporal and spatial fluctuations occur, is the interface region here. So the focus of today's talk and of pretty much the whole workshop is what's happening in more or less this region. Where that exactly is depends on the effects you're trying to identify. In this picture, taken from a recent paper, this is a relatively small region of 2 to 5 angstroms. Maybe you have to go a little larger, depending on the system, etc. But that's where all the science plays. there's a couple key concepts I want to just mention up front, and then I'm going to go through several of those step by step and go through some of the equations that arrive based on these ideas. So we're going to have a dielectric continuum. We're removing the need for explicit solvents. That's what we call the solvent. The electrode, I'm going to typically call the solute. That's based on chemical engineering or chemistry language. There's a solute dissolved in a solvent. But in our case, when I use the word electrode or solute, think about it the same way. When I say solvent or electrolyte, I'm also mixing those words up depending on the context a little bit. That's your fluid. The electrolyte, then I'm emphasizing the ions. If I just say solvent, it's just the fluid. Maybe there's electrolytes in the, ions in there, maybe not. Right? So I apologize if I make that too confusing. I'll try to minimize that. And then we have different energy contributions we have to consider. There's first of all the electrostatics that matters. And so we're going to see that this is going to lead to the Poisson or Poisson-Boltzmann equation. I'll say more about that later. We also have non-electrostatic energy contributions that matter. That one of those is, for example, if I take an ion and put it in a solvent, there's a cavity that ion lives in. It has to form that cavity. That actually costs energy to create that cavity we put the ion in, simply called the cavitation energy. Then there are van der Waals, like dispersion interactions between our solute and the solvent. So these are not electrostatic in the strict sense. They are fluctuating dipole interactions, etc. We're going to have to put those in explicitly. These are interactions which even density functional theory itself has its own issues with. So they need to be dealt with explicitly. And then there are repulsion terms in there which also need to be treated explicitly. All these terms are often treated empirically. So we're just coming up with some approximate form, maybe some numerical parameters to figure out how large are they, and then tune them to specific quantum chemistry, quantum mechanical calculations. Sometimes they treat it semi-empirically, really depends on what we have available. There's two types of equations we're going to encounter. There's going to be the Poisson equation here. I'm going to call that the inhomogeneous Poisson equation because epsilon is not a constant. It's varying with space. This is going to be typically our dielectric constant. We'll treat as 1 inside our electrode or solute, because there we're doing a quantum mechanical calculation, and there's no extra epsilon. That epsilon comes out of the quantum mechanical calculation. And then in the solvent, our electrolyte, we're going to put the epsilon in at 78 for water. And that varies spatially, obviously, in some form. And we've already seen in Jörg's talk earlier on that epsilon can be, 1 over epsilon in his case, can be positive and negative and go to 0. So those are the kind of fluctuations you may have to build in when you construct your epsilon in the Poisson equation here. Phi is the electrostatic potential. Rho is your entire density of charges, positive and negative charges in your system. And on the right here, I'm going to show you what the Poisson-Boltzmann equation looks like. And it's essentially the same equation, except for we have the ion charges in here. And the approximations that are made in the Poisson-Boltzmann equation for the dissolved ion in the electrolyte, I'm going to talk about that, has to do with entropy and assuming the Boltzmann distribution and other things for that. Yeah, I already talked about the cavity formation. The cavity has to be solute shaped, so it's going to push the electrolyte or solvent out of the way. And there are different ways of how that's typically implemented. Historically, in the 80s, it was first simply defined out where are my ion or solute positions, and then we're going to draw spheres around it with hard surfaces. This is the excluded volume where the solvent or electrolyte is excluded, those hard spheres, and then you form the union of the hard spheres. Gaussian still has methods like this built in. More modern techniques base that, for example, on the electron density or something a little bit more complex, where the electron density of your solute or solvent drops. So your quantum mechanical calculation shows the density is dropping below a certain value. At that point, that's where the solvent can approach, and that forms a cavity with a diffuse interface in those cases. I have a button here. Okay. I'm going to take here a specific perspective on developing these implicit solvation models, and that is really motivated historically by the power of density functional theory. I'm going to take a functional perspective here, and an energy functional specifically for that implicit solvation model. That doesn't mean it was historically derived. I'm going to say a little bit also about the history of solvation models, starting in the 1920s all the way to now. But this energy functional perspective helps us to directly link with conventional electron Cohen-Sham density functional theory, and then also with the classical DFT later on. And it also puts the whole idea of solvation models on a very foundational basis, that we really have an energy expression, and we're going to just have to do the minimization of the energy expression to obtain all the equations we need to refine these approaches, or no, to numerically solve these approaches. And then we have a systematic way, by improving our energy functional, adding an extra term to it, and making sure they're really quantum mechanically motivated, to improve, in fact, the equations we solve and our implicit solvation models. So the implicit solvent describes the thermodynamic system. Right? It's that solute, which we describe quantum mechanically, the interface, and the continuum solvent. And we have to write out the Gibbs free energy for that case. And the Gibbs free energy is going to depend on a number of variables. Here I'm just illustrating two of them. One is the charge density. That could just be, you have a question already?
Yeah, because my question is a bit, is this a grand canonical system? Is it thermodynamically open or not? Because if you use a Gibbs energy, it would be a closed system or a canonical one. So the question is a bit, you probably know already where I'm driving at, also would it be the grand potential or should it be the Gibbs energy that we're using there? Because what is really the, let's see, quantities is the chemical potential, or is it the number of water molecules that is fixed?
So that's a perfectly sensible question. The good news is in thermodynamics, it doesn't matter what you use. You can always use any functional. You just have to be a little careful when you do all your transformations. Do I need an extra Legendre transformation to get to an omega or capital phi for the grand canonical ensembles? The literature always talks about the Gibbs free energy as this expression, and we've talked about that extensively yesterday. Maybe it actually should be the grand canonical potential. I'll have to think about that a little bit more. This is a very valid question, and I don't want to glance over that here right now, but I don't have a clear answer for that yet. But when we look at all the energy contributions we're going to put together right now, many of them will not actually depend on if it's constant n or constant mu. Right? If you look at some of these expressions, they will be unchanged because they're not explicitly depending on that. So those don't matter. And then we have to just be careful in the end. Do we keep it as an open or as a closed system? And we can always transform one to the other. Right? So the whole derivation would work with any thermodynamic potential. You just have to then transform it in the end into one that is most convenient for using.
I guess it could become interesting if you really ask then for particle exchange, if you want really to connect your chemical potential. Yeah. Is that of adsorbed hydrogen and so on? So then you could really have something.
It really depends on how you use it in the end, because the implicit solvation model doesn't depend on how you use it, right? So I can do a simulation in a canonical, in a grand canonical, in a microcanonical ensemble, and I'm going to use the same equations I get in the end. The derivation I'm showing you here today really just assumes these are Gibbs free energies, but you're right. You might want to see if you apply it in a grand canonical sense. Are there any other terms or changes to the thermodynamics needed? It's a good point. Yeah. So maybe when we get a little more explicit, if you see something, hey, here it would make a difference, let's talk a little bit more. So we're going to use one of the thermodynamic potentials, the one I like the most, and I always tell my students in my thermo class, the Gibbs free energy is the answer to every thermodynamics question, right? So it's the thing you minimize under constant temperature and pressure, and if you want to solve a problem, you just have to figure out what are all the contributions to the Gibbs free energies, and that gets you 90% of the solution already. And I think that's the same here. There may be one additional Legendre transformation we can do at the end to get to constant chemical potential versus constant number of particles. And then once we have these expressions now for the Gibbs free energy, now come, my pointer here. Oh. My Gibbs free energy here will depend on the charge density. We're going to see that in most of the expressions, this will just be the charge density of the electrons in the quantum mechanical solute electrode region, and we have the electrostatic potential. When you got the Gibbs free energy depending on multiple variables, and you got to minimize the Gibbs free energy to get you to the thermodynamic ground state, you have to do variational minimization with respect to all these variables. And so when you do that, that's how you're going to actually obtain the kind of equations you have to implement in your DFT calculation. You solve, you end up by setting the variation of G with respect to both variables to 0, get your Euler-Lagrange equation. And let's look at a simple example, and I'm going to then actually extensively talk through how we really do that for different kinds of electrostatic models and stuff like this to obtain Poisson and the modified DFT equations. So that total energy functional typically consists two Gibbs free energy contributions. You've got the energy of the DFT, and again, I'm writing E here. This could also be, thank you for your help, this could also include some free energy contributions for the electrons, that could be some other contributions, etc. I'm just simplifying it as EDFT as a function of the electronic charge density rho. And then we have our contribution to the Gibbs free energy of the solvent, and this could have a variety of contributions. We've already talked about it. The first one is some electrostatic contribution. We've got the cavitation Gibbs free energy. We've got dispersion interaction of our solute with the solvent. We got some repulsive energy terms potentially, and if we have an electrolyte instead of just a solvent, there's also the Gibbs free energy of the ions as part of that. The Gibbs free energy of the ions will definitely depend on the electrostatic potentials. The others may not. Okay, so there's a hierarchy of these energy contributions. Already mentioned that here. We've got the electrostatic energy that is largely dominated by the solvent polarization. The Gibbs free energy of the ion, the last term, is going to introduce the ionic entropy. It's just the ideal entropy of mixing for ions at a given electrostatic potential. That contains the ionic shielding in the end. That includes the double layer formation. The work to introduce the cavity in our solvent is in there. That defines what kind of solute-solvent boundary you have, van der Waals attractions, short range, solvent exclusions, all important. And so many solvation models differ by the way they treat various of those terms. Many models, especially the ones in the quantum chemistry, originating in quantum chemistry, have an awful lot of parameters for these different terms. For each different species in a solvent, they introduce different terms in different solutes as well. And some of the more advanced models actually have fewer parameters. Salsa is a model which has very few parameters, for example, for that. And they try to derive most of these variables based on physical principles rather than making parametric expansions.
Do you have contributions that includes then the pressure? Because I guess the pressure would also correlate then with the number of water molecules. Because you have the cavity formation.
Well, water is a pretty incompressible fluid. Yeah, so pressure won't do much, but still, yes. So all these terms in principle depend on pressure and temperature.
Yeah, because that would definitely tell you, because the cavity, if you see, you have essentially incompressible water, so all volume which is eaten up then by the cavity should really be water molecules, or let's say the water volume, and then you can see whether this changes or not during your calculation. And then you would see whether it's grand canonical or not. You see, if I calculate essentially then...
I don't think the pressure has anything to do with the number of molecules we consider.
No, not so. Let's see, if I say so that it's incompressible, then of course, so if I would, let's say, add then something like a cavity, I would need infinite pressure, but therefore I expand my volume. So, and I would get then, so I can measure then essentially your implicit water. So you have then this cavity region, and I can iterate in order to get then the volume. And if I assume then that it's incompressible, so then the volume should directly correlate then to the number of water molecules that I've in there. And then I can see if during the course of my simulation, my volume of the implicit solvent changes. That would mean that this is a grand canonical.
Yeah. So the question is effectively, when we look at a process like a chemical reaction at an interface, we're going to have these cavities, and if these cavities are defined, for example, by the electrostatic conditions where my electron density drops to 0, and that volume changes effectively throughout that reaction, that would mean the amount of water I have in my system could also change, or would change, and that would mean essentially the number of water molecules in a system, if I had a fixed volume, would actually change. Since this is an implicit model, it doesn't actually have a volume in the end in that, because the volume that's taken up is essentially arbitrary in that point, right? So I don't have a specific constraint. My volume would essentially, the way I would envision that, I've been told I should write on this side.
Your supercell, you have a well-defined...
It has nothing to do with the supercell. Remember the implicit water? The idea is essentially that it extends infinitely on the side. Where I draw that boundary now is an arbitrary choice for my thermodynamics. How it's mapping on the calculation is a different question. But from a model point of view, this is my electrode, for example. And here's my semi-infinite, and this should be, both of them should be, in the way the model is designed, semi-infinite. Here's my water. Here's my electrode. And here's my cavity happening. Until that cavity shrinks, more water essentially approaches this. This is semi-infinite, it doesn't matter. I'm going to just make it a little smaller, effectively. So I don't think that affects the derivation mathematically, what I'm doing here.
So much the derivation, I guess.
When you map it, of course, on a real calculation, then you might have to worry about that, right? But I don't think, since the water doesn't contribute any energy here, if I have more or less water in the implicit model, again, it doesn't matter. I don't think there's any, in the implicit model, there's any extra energy contribution term I'm missing from that work that my cavity gets larger or smaller. Right? But we should talk about that. I think there's no extra term.
See, I guess you're right, because I guess what one assumes is that's a chemical potential for the water instead of bulk water.
Yeah.
That's essentially what you assume, and then it's...
So there's nothing happening at zero, right?
There's nothing happening at zero, and therefore
we're
you
good.
don't care.
But from a derivation point of view, right? But just because we know how to derive it doesn't mean that we apply it in a real calculation that we're doing the same thing, right? So it's a good point to keep... In general, it's a good point to actually, as clearly as possible, always write out your assumptions you made when you derived this stuff, because when you later apply it, you shouldn't forget what you assumed early on. Right? Many of us have probably made that mistake, and then are surprised, like, whoa, this is different. So you've got all these contributions. Does that, okay for now? And yeah, I talked about that there's models, some have more parameters, some have less parameters for that, but unfortunately, many of the models have an awful lot of parameters. They're empirically determined. That means they can also be quite accurate, but once you're outside of a domain of applicability, they fail. And I'm giving you an example later for that, from one of our own work, where applying it to other solvents is a disaster, but it's a fixable disaster. Okay, so we have the one expression which is simple, and most people don't argue about it, is the electrostatic energy here. The electrostatic energy for a liquid is simply given by the dielectric constant times the gradient times the electric field squared, integrated up. And that is in some specific set of units here right now. There may be pi's missing. And when we minimize that expression, which explicitly depends on the electrostatic potential, minimize that with respect to the electrostatic potential, you're going to immediately get out the functional derivative of that is simply given by minus the gradient or the divergence of the permittivity times the gradient of the potential minus the electrostatic, minus the charge density has to be 0. Puts it on the other side, and you get the well-known Poisson equation out of that. So the Poisson equation tells you, normally we write it out that's the Laplacian of phi equals your charge density, but when the electrostatic, when the permittivity of your liquid is not a constant, you got to keep that inside of your divergence there. And then once you have that equation, you know what epsilon of r is, you just got to apply the right boundary conditions and can solve that. And most plane wave codes, I'm not going to say more about that later, but I can talk about that. Of course, use plane wave expansions for that. Turns out that these operators have a very nice form in reciprocal space, and essentially it's just multiplying with k and stuff like this, and you can solve these with fast Fourier transformation.
So error in the sign, the typo?
Say that again?
The sign, is there a typo of the sign?
Typo? There could well be typos in there. Oh, there's a minus too much, right? Yeah, there's too many minuses. I think this minus needs to go, right? Yeah, thank you. These slides are pretty brand new. So the concentration of typos is an exponentially decaying function, and we're at the beginning of that. This I just created on Sunday. That was yesterday, right? Yeah, no, Saturday. So please correct any typos you see in there. To give you an example, I taught my thermodynamics class this morning, and I had a minus sign in there wrong too, and I've been teaching that for 6 years. Nobody had pointed that out before. I look at the equation. Why is there a plus PV? It needs to be minus PV or something like this, right? And it's terrible. Sometimes I think the computer just changes those over time. Okay. So that is the Poisson equation you obtain simply if you have that simple electrostatic model I just had, that it's just, we have just a solute in there. And if we now add ions into our solvent, and turn it into an electrolyte, we need to worry about where do the ions sit, what is the concentration of ion as a function of position. And so the simple model there is, you got some local electrostatic potential. That means when you put an ion into that local electrostatic potential at that point, it has a certain energy, which is a charge times the local potential. And then we're just assuming it's a Boltzmann distribution. Right? There's an e to the minus the energy of the ion divided by kBt times some reference concentration C0. That gives me the local concentration of ions at that point. And when I first learned about these kind of models,
what is your CI0? Is this now?
That's just the reference concentration for the ions, the maximum concentration we can
water
have.
Molecule? I'm asking a bit
of the ions. That has a subscript I for the ion in there. It's the concentration, the maximum concentration of ions I can have in my model, in my solvent.
Determines this. So I'm asking a bit what Manuel was saying this morning.
That's a parameter. It's an experiment. It's a parameter which has to come from experiment. This has to come from experiment.
Okay, so this includes then this exclusion volume Manuel was talking this morning. So
this has to be the maximum concentration I can obtain, because when my T goes to infinity, I get to that maximum concentration.
It's not, so my question was mainly, it's not related then to the number of, or let's say per water molecule, because then you would get V too high.
It's not 55 molar.
Yeah, or even less, let's see, so that it would be, it's not
it definitely depends on the ion. There's a CI0 in there for a reason. It's the reference concentration, the maximum I can realistically arrive. Where that really is and how we do that experimentally, I don't know. But thermodynamically, that's remember, this equation is this equation here is an assumption. We assume that our local concentration depends, based on the Boltzmann distribution, only on phi and the charge of my ion, Zi times E. Right? And there has to be a reference concentration in that. So to map that onto real systems, you have to essentially fit your CI0s to some data.
What about the dielectric constant of water? So you have now Zi times E, so that would be the unscreened, or I'm not really sure.
No, there's no screening. There's a local electrostatic potential.
This is a local.
That's the potential at that position. Maybe that's what I forgot. These depend on R. Right? This depends on R. This depends on R. Everything else just depends on nothing. So this is simply the energy. I'm an ion. I'm sitting in a position in space. There's a certain potential. I have a certain energy. We're assuming in all these models that it's just the Boltzmann distribution. It's classical particles. What is in thermodynamic equilibrium, the concentrations of ions at that point.
But for the ion concentration, I guess you include then your dielectric constant. You must.
For the what?
For the ion-ion interactions, the term you had before. So if the ions are interacting, so they are interacting via the dielectric medium. So if you make sense the Ewald summation. So there must be.
So there's no Ewald summation here.
Well, there must be. If you go not here, not here.
This is a charge density in the field.
No.
I don't have any Ewald summation. Before I don't have an Ewald summation either. If
you go then to the energy contribution, so you had then an ion.
This one?
Yes.
No, I don't have anything in here. There's no ion in there either. These are fields.
You don't have any ion-ion interaction in there, so the ions are not.
Yes, they do. The ion-ion interaction is in the electrostatic term. Let me sure I go to the right slide. The ion-ion interaction is here.
Yeah. Okay. So via the.
There's an epsilon in there. That's correct. So the ions will interact via the local epsilon again. It's all in there, but these are all smeared out. There are no point charges left anymore. So at this point, I just have simply the electrostatic average charge density of my ions in the water. My water itself is just simply described by that, right? And then I have, of course, what happens in the solute.
But it really means so the ions would be screened by.
So the ions it's a smeared out picture, right? And so the local variation of epsilon around each ion is not included in these models at all. right? So this assumes that I've got some sort of epsilon, and that varies with R, but it's all smeared out. It's already thermodynamically averaged. And when I look at these energies, you have to be very careful there. I think there's certainly a spatial variation that's missing.
Yeah. So I guess, yeah, so if you would really want to compare then the energetics, so you would be missing because it's like these
The ion-ion interactions in a real system has an ion, a nice little solvation shell, the little oscillation we've seen earlier, right? There's another ion here with that little oscillation around it. In the middle might be a little bit of water with indeed the epsilon of 78 or smaller. And when you put these close off further together, it's a function of concentration. Can be complicated.
Yeah, but first order.
So that in this model, it's all smeared out, and all those variations, which are in the real system, have to be captured by the Poisson-Boltzmann model by varying some of the parameters you have in there. They have to effectively describe that, but explicitly, the physics of that is not in here. Other questions? This is good. These are good points.
In the equation that's implemented in joint JDFTX, at least, there is a screening, there's a cavity modulated screening constant.
You can put those in. So JDFTX has a lot more terms in it because it's based on, at least in principle, on classical DFT. So that's a good point. But in the simple models I'm introducing now, we're not doing that. Later on, I'll say a little bit more about the salsa model, which also tries to do a couple of things. And there's certainly what's in some of the models, the VASTSOL has also implemented is some terms which some finite volume exclusion of those ions near the interface, which kind of emulates some of those things. Is that what you're also talking about?
I was just talking about the solution of the Poisson-Boltzmann equation itself. There is on the left-hand side of that equation, there's a screening, like a cavity-dependent screening that's subtracted from inside the brackets of the divergence.
So from inside the epsilon, there's an extra little term, there's a term subtracted from the epsilon?
Minus kappa squared SR over there. And then that equation is variationally solved to get the charge density.
Okay. I think that might actually happen also in the regular models. We can talk about it afterwards to make sure that when you actually plug in all the terms for rho I and what that is, you can actually move some of the stuff over and there's a kappa term, right? The by screening links, right? Is that what we're talking about? Yeah, I think that happens also in the Poisson-Boltzmann equation. I'm written out the simplest form of that. And I haven't actually completely written out because what you next do is you're going to take this term, you put that Ci in here, then you take, that gives you a rho I in here, and there's an extra term. There's an extra the Gi in to also take this expression and plug it in here, and you got two contributions. One is that rho I in here, and then the T times S term for the Gi in matters when you do the energy minimization. That you get an extra term in the density functional calculation from the Euler-Lagrange equations for that as well. So let me say a little bit about that. I actually don't have a slide on the kappa because I've just kept it a little simple. What we're doing here right now is a general, completely nonlinear Poisson-Boltzmann equation, right? You get these kind of terms, and there is a version of that when you actually linearize that. For low ions concentration, you linearize these expressions, and then you get the Debye screening lengths in there instead. And then you actually end up with a minus a kappa squared, some kind of sort of stuff on the other side here. And actually, the problem is a lot simpler to solve. I didn't write that out here. That's implemented in VASTSOL, in JDFTX. I'm sure there's a version which does the simple one and then the more complete version. So the linearized version, you get a Debye screening lengths. This is supposedly only valid at small concentrations, but the small concentration can be surprisingly large because you have to look in the right space what small means in that case.
Looks the way you write it now, so you must have then an absolute figure, because it would really, so if I change the potential by a constant, I would then really get a change then in the constant.
You change the CI0. That's a typical transformation. The reference is absolutely irrelevant as long as you change that along with it.
You have this as function of phi. This looks really weird.
No, it's not a function of phi. It's a function of phi 0 for your reference.
Yeah, sure,
This is a reference concentration which depends on this reference concentration, but that's just always happening in thermodynamics.
No.
Uh-huh.
No, never. Normally you really have always...
That's the equation for the chemical potential.
Yeah, but normally you would then really put this inside. You would then write E phi minus phi 0 and never...
Let's put my I's on there, I 0. This depends, of course, on the reference. This is a reference,
Sure.
and it will change the reference
Yeah,
of
but
that.
you would write it then in this way so that you...
It's the same way, it's the same equation.
It's the same equation, I agree, but you would not write it so.
But there are natural references, which makes sense, and then the unnatural references, but it really doesn't matter. In the end, mathematically,
Mathematically, it doesn't matter, but
one affects
physically
the
it
other.
matters. So how you write it?
Oh, physically it matters because we're making certain assumptions about the reference
Because
makes
you would
sense
really
to us.
like to have, let's say, then something like, because in the morning, so we had this exclusion for you. So this would give something
So
very
the way I've written out that equation, if that is the maximum concentration, then the assumption here that energy is really zero at the right potential, right? So for an ion, the energy can only be zero when the potential is zero. So it's an absolute reference in that. And then it would correspond to the maximum concentration of ions I
Because
can
what
have
you
in
have
that
now
volume.
is in something like the CI0 would be the CI00 times E2 minus mu divided by KBT. Then you could
No, not mu.
Oh, not mu is
Mu zero.
E.
There's a mu zero in
E
there.
or
Again, it's just a reference.
It's a reference, yeah, sure, but it's a phi zero. So what you have
There's a phi zero, there is a Ci zero in there.
Yeah,
That's
but
right.
this is, yeah, it's in there, but you can also put, okay, let's talk about.
But where do you put your reference is really 100% up to you. It changes none of the physics. Other questions? So you get a Poisson-Boltzmann equation. You can, in principle, linearize it. When you linearize it, you get the Debye screening lengths. Thanks for all those questions. I wasn't actually trying to go into that because I don't want to confuse everybody. The most important thing is you got your energy functional expression. You're going to minimize this with respect to the variables that are relevant, the charge densities and your electrostatic potential. Get an Euler-Lagrange equation, which look like those equations you've seen from electrostatic Poisson-Boltzmann equations. And there's a lot of pretty strong assumptions going in there, especially that Boltzmann distribution, etc. Ideal entropy of mixing. I haven't even said that, right? This is the ideal entropy of mixing, X, ln X. I asked that in one of the earlier talks. These, in principle, this entropy expression is a mess in real system because you have activation coefficients playing a big role in stuff like this. Nobody, as far as I can tell, includes that in the solvation models, right? We include that in all the thermodynamics, all the phase diagrams and stuff like this. We ignore that here quite heavily, and there may be something to be said about including that. Unless you had very small or high concentrations, that's not necessarily valid. Okay. There's another approximation we always make, that's almost always makes, we can get beyond that, and that is a linear approximation for the polarization relative to the electric field that is just simply given by that expression. We can go to nonlinear polarizability models that epsilon also depends on E. That is important because if you think about a pure water molecule, we've already heard that in some of the earlier talks, we have two contributions to our epsilon. One is the dipole moments. All our water molecules can rotate around relatively freely. That takes some time, but they can do that. And screen our electric fields. But we can also shift the electron charge relative to the nuclear charge to the electronic polarization of our molecules. That's a very fast motion we can do. And both of those two effects have different time scales and different dependence on the electric field. The electrical polarization works pretty much at any electric field accessible in these kind of systems, and it's pretty much a linear relationship. The dipolar polarization, if you make your electric field moderately large, the dipoles at some point have oriented themselves all in such a way that they screen the field. Once they're oriented, there's nothing I can do. If I increase my electrical field any further, I'm already done. What can I do? At that point, the dielectric constant or permittivity here of the dipolar contribution essentially goes to 1, right? And that means the difference, it just drops out. And all you have left is the electronic polarization. In other words, what you're going to get is that your effective dielectric constant, epsilon, depends on the electric field and goes from 78. So this is 78 up here, and it goes to what is of the order 2 roughly, right? For water. It drops as a function of the electric field. So the models I'm showing you today ignore that effect. You can put that in. Simply just have to add this kind of functional form in there, how epsilon also depends on E. It's not a big deal, but it's numerically certainly an extra set of iterations you have to do to make the solutions self-consistent. But what I really want to point out here is now, we've got now an energy functional. I've changed my rho to n. I had a little trouble in PowerPoint to get the equations typeset with retypeset. So this is the charge density of the electrons in the solute. This is the electrostatic potential everywhere. We have our normal DFT expression for kinetic energy and exchange correlation. The term, the electrostatic term, I don't have in here because the electrostatic term is over here. I've separated that out because I'm changing that now. So here's your electrostatic term, is your potential times your charge density of solute and ion, and clearly this is rho, this is actually on purpose, because it contains the electrons and the nuclei in my quantum mechanical region, integrated over all space. And then I have extra terms in here. I got the term for the interaction of in my dielectric. This is called the bound charge interaction. This is my polarizable continuum here has an energy of epsilon r times the electric field squared. And then I have my cavitation energies typically in there. This is how large do I make my cavity. If I make it larger, I'm assuming here right now that the cavitation energy just depends on the surface area. It turns out that for small systems, that's not very accurate. There's extra terms showing up there. In large systems, that's pretty good. It turns also out that this overall is a relatively small energy contribution. Tau is a pretty small number. And then I have my entropy of mixing for the ions in my electrolyte. Those are the main energy contributions we typically consider. And if you then minimize that energy expression with respect to the charge density, that's the first minimization we do. The other minimization we do was the electrostatic potential. I already showed you get the Poisson-Boltzmann equation. Now you get essentially your Cohen-Shem equations out of that. Kinetic energy of your Cohen-Shem equations, some external potential. There is, that's your electrostatic terms. That's just the Laplacian of your electrostatic potential. I'm a little confusing myself. And then you get, so this is what you normally get in DFT. These are all extra terms from your solvation model. So in your DFT equation, you have to implement these terms into the Cohen-Shem equation when you solve for them. These give extra potential contributions you have to solve for. So you got your dielectric response. You got the change of the cavitation energy with respect to the charge density. If your cavity depends on the charge density, if it just has a hard sphere cavity depending on the radii of the atoms, that thing drops out. And in general, that's not a huge contribution, but it's an annoying contribution. It's one which is actually extremely sensitive to calculate, by the way, because it depends on the mesh sizes in your DFT calculation. And then you got your Poisson-Boltzmann ion contributions term here, depending how that's changing with respect to your electron density.
Good question. So you mentioned tau a cavity, the term is not very accurate when the feature is small.
Yeah, tau times A is an approximation. So if you have very large system, really it should be the surface area, but for smaller ones, I think.
Which is the error? Like, is the assumption that tau is constant?
Yeah, well, effectively the assumption that tau is constant in that equation, that it's just the area that's changing. So one could say that tau changes with radius or area, stuff like this. That would be one way around it. Or you just simply say there are terms in there which are not proportional to area, but proportional to volume, for example.
So tau, it doesn't have to just make it A can have D tau and or something like that. They do that.
No, I think.
You see what I mean? Like, is it the assumption of tau being constant is a problem, or something else?
Well, that term, the cavitation energy, we have to come up with some functional expression in order to parameterize it, right? So this is a term which, for example, includes, in many models, this kind of term is assumed to take over the van der Waals interaction between my solute and my solvent. It includes hydrogen bonding between the solute and the solvent. It includes the energy required to actually empty a little bit of space to put a solute into the solvent. So all these contributions are in there. Since most of these interactions, the van der Waals and the hydrogen bonding, should be proportional to how much surface area my cavity has, because there's the number of interactions, the tau times A makes sense, right? And it's dominating, that term is certainly dominating.
Constant is not quite right.
Yeah, essentially that's what it means. And then if I keep that expression, you could assume that tau being constant is not the right assumption. Or you could say, let's spread out all these energy contributions into separate terms. Which of them have only a surface area contribution? Which of them, for small surface cavities, where the curvature gets large, get changed and stuff like this? I mean, even the van der Waals and hydrogen bonding interaction, when the cavity gets small, at some point they discrete the number of interactions I have, and maybe there's some nonlinear happening. So this is not a term that always just depends proportional on the cavitation area. There's other contributions that can play a role. But overall, at least in the models I've worked on, the tau is such a small number that we actually recommend, for example, in our model, when you do electrode interfaces, just set it to 0, because the numerical noise that term causes is more annoying than that tiny little shift in energy. And it's usually within the statistical noise of our method of what that term does. That's not true necessarily for all methods, but yeah.
So here you assume, I guess, that the number of ions is constant. So this would be canonical, because you have only an entropy contribution, not one where you would have. So in principle, you could also extend it also that you could really see I have now a chemical reservoir then for my anions, for my cations, which would be interesting, could be interesting.
I think this is the same assumption that we got that semi-infinite, and we'll just move things in and out.
Different, because here you could now really get an additional charge or so in there, depending on what surface dipole you want to have. So I have the feeling it would be very easy to introduce it. And because then for the water it's easy, you would have essentially the assumption so that the water chemical potential is always that of bulk water. But here you want to have really...
Well, here the assumption is that the ion concentration far away from the interface is also just constant instead of bulk water, right? But then, do I draw the boundaries at the same region and stuff like this? It's a good point.
Yeah, but here it could really change then, the chemical potential inside. So if you have then something where you make the surface then more attractive for anions, so then you would like to get more than really coming into your system.
Yeah, but I have a semi-infinite reservoir.
No, but this is exactly what the chemical potential would tell you. So you have a semi-infinite reservoir, but in this equation, the number of ions, the concentration is fixed. So you have only the entropy in there. And in order to really capture then the semi-infinite character so that you are bound into it, you would need, I think it would be super easy, so that you just add then something like a chemical reservoir.
Yeah, no, the expressions aren't hard, right?
They are not hard.
Let's think about that. I think we should definitely sit down and go through that and make sure there's something missing.
I think that exists. The grand canonical formulation, it's just a minus mu n.
Exactly, so that's what I would,
Does it make a difference in the end?
This is the Helmholtz free energy variational functional. The grand canonical for the grand potential energy is just this functional with a minus mu n. That already exists.
Okay, yeah.
It doesn't make a difference in the implementation then in the end?
No, it's just a subtractive term in front of it.
It's
Legendre transformation. It's changing the reference again or something.
It's a Legendre transformation.
Yeah, I know that it's a Legendre transformation. That's not the point. I'm just saying it just shifts the reference point, right? Yeah, for that it matters. And you can do that by hand afterwards, I guess, in our method.
You would change then the number of ions, so you would change the entropy. Because if you have now, let's say, a situation...
We don't change the entropy. Sure. The entropy is given by the local concentration.
Given by the local concentration. But if you fix the chemical potential, and you have now a reaction or so, which is changing...
I think you change the chemical reference, you change the reference potential again.
So that if you have, let's say, a fixed chemical potential, so now you have something where you are changing then your inner chemical potential. You would get then, and therefore you need this n times mu terms in order to get more in there, then you would change, of course, then... Yeah, so you would then change then also your entropy. So this is what exactly is done then, if you add this term. And it's straightforward, so I think we should really sit down and...
The Legendre transformation isn't hard, right? I think it's just changing your Fermi level, like you're describing essentially in the end, and that you can describe also without adding that,
change
term.
Also, really, so that's what...
The entropy doesn't change because of that.
Because if you change...
The ideal entropy of mixing just depends on the local concentration.
Exactly, but you change the local concentration.
I don't change the local concentration.
If you have a chemical potential, and I've changed here the chemical potential, what's happening then? So then atoms are flowing in there, and if you have a grand canonical approach,
But I have the right concentration.
you
It's the
don't have
Boltzmann
no,
factor.
you don't have. So that's the main point. So that you can see. So if you are working,
Let's talk about that afterwards.
So that's
right?
really the difference between the grand. So then you are fixing the chemical potential, and then of course in a grand canonical scheme, your local concentration changes or can change. And if the local concentration changes, then also the concentration.
My local concentration is simply given, just to come back.
Yeah.
This is what my local concentration is given. There is no chemical potential of the ions explicitly in here. That Ci0 I can clearly change and stuff like so. I can define what concentration I have in my water. That's fine. But this is simply given by phi in the end.
I think we agree, or if you change the pH, or let's say if you have then outside a given chemical potential, if I have now then
my concentration of ions in solution needs to be specified. I agree.
Yeah,
and this in a semi-infinite reservoir, I do that. And I do that in this with these expressions here. Right? It doesn't have to be grand canonical for that.
Let's write it down. So I think it's a good exercise.
Okay. I agree. Okay. So I mentioned that we're using that energy functional approach because it provides a first principle rational for the model construction. It allows you to self-consistently couple the expressions and the equation in the end to DFT. It works with all the variational methods that have been implemented in DFT, and supports extensions in principle. This is some of the things we want to do in the workshop to account for various exothermodynamic terms, maybe the grand canonical stuff, and the extension to dynamics, fluctuations, and as done in some of the methods like Candle, Salsa, JDFTX, to non-local effects. I want to give you a little bit of history of where it all started, the solvation models. And so the solvation model started with Born in 1920 when he actually wrote out in an article the energy of an ion, of a charged sphere in a dielectric continuum. So young Born over there, first equation, very simple. Onsager modified that. He calculated what happens if it's not a point charge, but if it's a polar solute in a spherical cavity. So this thing has a dipole moment mu in there in a cavity, and he calculated the Gibbs free energy for the polar solute in a spherical cavity. And then Kirkwood modified that further by accounting for the orientational correlations in those polar solvents, and then he gets the average of the cosine theta ij between neighboring dipoles in there as well. Other than that, you already see there's the same mu squared equation in there as well. So those are the first 20 years of implicit solvation models. So relatively rapid progress with very fundamental stuff, but then there was a sizable gap. So in the meantime, Hartree-Fock, DFT, quantum chemistry were invented, and so science came back around in the year 1980. In the 80s to 90s, solvation models, implicit solvation models, were first implemented in the Gaussian code by Tomasi and Persico, which introduced surface charge-based solvation in these cavities. So what they essentially did is they made the cavities with hard cutoffs, and they considered surface charges inside that cavity to describe the solute and introduced energy expressions into the Gaussian code to calculate the solvation energies for those ions and or solutes in solvents. They had sharp boundaries, and so one of the problems why DFT didn't, when solid-state physicists wrote their codes, didn't look at these models because the sharp boundaries is something we don't even touch, right? You can't use a plane wave code to resolve sharp boundaries. So they were not compatible with plane wave DFT. And they also were somewhat limited when the systems were charged or very asymmetric, or when the charge state changed of anything inside those things during chemical reactions. So they were really the first step. They were a dramatic improvement of the Kirkwood, Onsager, and Born models, but they had limited use for real chemical reactions, etc. So things changed. There was another 10-year gap from 1990 to around 2000 where these models were certainly improved with more parameters and stuff like this, but not much dramatic in the sense of methodological development. In the early 2000s, Vatterberg and Gigi came up with a couple of very important concepts for solvation in the sense of for plane wave DFT codes. Francois Gigi had its own plane wave DFT code, and what he introduced was a smooth dielectric cavity, making it a local function of the electron density. So where the electron density is large, We don't have water. That's where our solute lives. When the electron density drops to small values, that's where the water molecules can approach. That's where epsilon starts going up from 1 to 78. And that was a major improvement. It avoided the discontinuities. It also enables you now to use a variational derivation of the electrostatic equation because your epsilon now depends on the local charge density. And so you can now derive variational principles and stuff like this. And then he introduced essentially the use of the inhomogeneous Poisson equation, where epsilon depends on n of r and implemented in the DFT code. Here's the 2 papers where they discuss it. And that really set the basis for a lot of good developments which keep on going on to this day. So there was work originally by Nicola Mazzari's group, which essentially used the Fatebe and Gigi scheme. They changed that switching function, so when the charge density becomes small and the cavity turns on, they use something numerically more robust. They also completed the variational approach to ensure that they get aqueous forces and stresses, so they included all the functional derivatives for the forces and stress, and they implemented that in quantum espresso. Around the same time, the Arias group at Cornell formulated, and I think I'm going to say a few things about that potentially tomorrow, a formulation which takes the implicit solvation models and puts them on a very clear scientific framework by formulating what Arias calls the joint density functional theory. That's a combination of the classical electron density functional theory we're describing. So I shouldn't use the word classical, that was a mistake. The electron density functional theory, which describes electron density as the underlying quantity, with another density functional theory which was simultaneously developed for liquids, where we use the density of the liquid as a quantity. And he calls that the joint density functional theory, where there's 2 densities, the liquid density and the electron density are the main ingredients. He proved, or his team proved, that you have the same variational principle as you have in DFT and can write out the equations, and you also end up with a functional, the correlation functional in those cases, which contains the electron density and the liquid density, which again is unknown. So it's very similar in spirit to the Cohn-Sham, Hohenberg-Kohn DFT, and the DFT for classical fluids. In both of those cases, we don't know those functionals. But that framework allows the Arias group actually to come up with clever approximation for how to separate these terms out and how to describe that interface. And they've developed, and Shankar Sundararaman, who might be joining at some point still our workshop, has been leading some of the functional developments here. Around the same time, our group also implemented a version of the JDFTX functional into VASP. It's called the VASP Sol. We've done that as a team. And we've done in 2019, we published the electrolyte extension of that same framework. And then more recently, Craig Pleasance from Louisiana improved on the VASP Sol method by adding the Stern layer, which JDFTX also has, the constant potential implementation in VASP, and some much improved numerical integration, especially relative to that cavitation surface energy term, which is a lot more stable than the original version we had. I want to say, I got a little more time, right? A few things about going beyond the local dielectric description. And this is something I'm not an expert in. I've learned about that from the literature by looking, so papers here, Sundararaman and Goddard developed that in 2015, which by trying to go beyond the simple form that epsilon just depends on n of r. So the traditional solvation models rely on that local dielectric function, right? The charge density becomes smaller and smaller. The local dielectric constant simply goes up. That's okay. That assumes that we got a local response to the electric field. Those regions over which these things turn on are relatively small. They're close to the resolution limit of our plane wave basis. We also assume that they're symmetric with respect to cation and anion solvation, which is not necessarily true. Shankar was able to go beyond that. So real solvents, as they showed, exhibit non-local correlations, and there's an asymmetric response relative to cations and anions. And that's seen in various experimental quantities, such as the interfacial capacitance. And so the starting point they took, because remember their formulation was they used that joint density functional theory, was to actually look at classical DFT and write out the solvent response, the induced charge in the solvent, as an integral over a susceptibility kernel, non-local susceptibility kernel. And then they make approximation for that susceptibility kernel and always get an equation for that induced charge density. So that has a lot more flexibility in it, and it captures more of the physics and produces a better dielectric screening effect. So rather than defining just that scalar dielectric function, SALSA actually focuses on that susceptibility expression here, and then introduces directly that induced charge density here, and keeps that epsilon 0 there in their Poisson equation. It's the same equation, but we make that local. That's numerically certainly fun, but introduces instead that numerically not so much fun susceptibility integral here. But so that gives them a lot more flexibility in the responses, and it also is, like I said, motivated by the classical DFT, and it works. So let me start with the illustration, because I think I haven't had enough illustrations, I feel like, throughout my talk. The linear PCM, so this is VASP-SOL and the implementation into quantum espresso and the various other codes. The linear polarizable continuum model I described earlier. Shown is here the response of water around a water molecule. I think we've seen that in Mira's talk earlier. There was that nice smiley, right? Here were the eyes, and here was that little smiley face. This is now fixing everything and just showing the response surrounding it. And what you can see here is that when you go from the linear PCM to your SALSA, you get a much more smiley face. It's much happier because it actually has more of that fluctuating response, the oscillating response Jörg also showed earlier in the solvent that's real in this system, that the linear PCM just glances over because it's really just a simplifying assumption to get solvation energies with as few parameters as possible. It gets accurate. It doesn't really focus on getting the dielectric response exactly right. So much more realistic looking. So, want to say anything else here?
So, Richard, do you know is one getting the first and the second solvation shells in this results? Because here it looks like I see only the first.
You get both. So you get the first shell is essentially this part you have here, red, blue, and then there's the second shell.
But that looks already pretty much isotropic, or?
No, afterwards it drops back to red. Here's another red layer. So you get a double. You get two oscillations.
I think it would be interesting to look really with respect to the explicit word also. So that was more pronounced.
I think remember this is based on classic DFT. So it actually does look at explicit water and calculates the susceptibility from explicit water, puts it in here, and it works. And the advantage of that, it's actually the paper calls it a parametry-free physical motivated model. Parametry-free means really that instead of having to make up parameters, we get them from ab initio simulations of your solvent. You obtain them from there. Your your susceptibility, and then your
So you're computing
response.
really from DFT the susceptibility with respect then.
You're computing
So there you must have
from ab initio MD, from the thermodynamic sampling of your explicit water.
Okay.
You extract the information about chi of R minus R prime out of that and plug it into this kind of
You do then
expression.
some kind of an MD simulation in order to get this.
This has to be done for every single solvent you have. You have to redo the ab initio MD simulation, or you could do classical DFT, whatever you do. You got to get your susceptibility measure out of for your solvent once, and then you're good.
Normally you would do this via perturbation theory, but I guess that's not what you can do with water because you have to integrate over all the different water configurations. So that must be pretty expensive then.
Well, you do it once, right? And you get your model.
For one model,
Once
like
you
you're
have your
saying,
chi,
so
for every solvent, you have to do it once.
like you're saying. So,
Not for the solute, for the solvent, you do it once.
yeah, but
Right? And you're good.
you could, but do you do it then for the bulk, for the cavity? So I'm pretty sure so it has also then some local effects. So if I just get the chi R, is this R minus R prime?
Yeah.
So it's really, okay, so this is then essentially only for the bulk because it is translation symmetry, so it's not really.
I'm pretty sure you get the chi for how the oxygen-oxygen interaction, the hydrogen-hydrogen interaction in bulk
Yeah.
correlate with this
Yeah.
function.
So for water,
right?
it's
So
fine.
this
But
is-
if I now destroy my translational symmetry by putting then a molecule in there and let this then solve it. So then, of course, it's no longer then R minus R prime. It would be R comma
It's still
R.
the same
No,
integral, it's just it's a boundary
It's a
condition.
boundary condition, yeah, but that's what I mean. So it would also change. So it would be then R comma R prime. Because then it really makes a difference. So whether I'm looking now at a point near the molecule, or if I go further away.
That's what's shown in this illustration. You're fixing the oxygen, you're fixing the hydrogen, and you calculate from your water. This is exactly
Sure.
what chi of R
Yeah.
prime looks like around the water
So for
molecule.
water molecule it works because this is really your medium.
This is what's in bulk.
Yeah, but
right?
if you would now have then
Now, if I put an ion in there, is what you're saying, what that looks like.
exactly, and then
Yeah,
it's no longer.
I think there you need to make some assumptions.
Yeah, you must
what
really
this
make
kind
some
of looks like,
assumptions.
right? Or you need to do some initial simulations and stuff like that and parameterize it. That's correct.
Content interesting, yeah.
I think that's a worthwhile approach. And I mean, the implementation exists in JDFTX already. Right? And
I
it's
guess
been
what
used.
we here for our application, so we really have to think about something R comma R prime. Because R minus R prime really means transition symmetry, or it doesn't really mean, so where I put it, it's only the second point. So the difference is interesting. If I have now an inhomogeneous system, what we have always for an electrochemical system, so that
No,
it's
always depending on the distance. I got my ion here.
Yeah, sure,
That's
it's
maybe
all-
my sodium ion. I'm looking at my oxygen ion or whatever else around it.
was not-
It's R minus,
sure.
it's the distance.
No. It's not only, let's say, so the formulation R comma R prime is more general. So it depends on the distance, but it depends also on the point where I'm measuring. Whereas if I have now water, so therefore it works for water beautifully, because it's a water molecule, everything is homogeneous, I can do it. If I destroy my translational symmetry, I'm no longer allowed.
Oh, you're talking about something else. I get it. Yes, thank you. So what you're saying is, if my water is actually now perturbed because I'm next to the interface and I broke my translational symmetry, I get it.
Yeah.
Then you need to worry about in my water correlations near the surface. It's going to be different than the water correlations further. I don't think that's in
No,
here.
it's not in there. So that was my point.
Right.
But I guess we have really to worry about it.
If you would put that in there, then you've done already all the DFT calculations. Then you wouldn't need to do the solvation calculation anymore. So that's approximated away. I'm pretty sure that in Salsa that's the approximation. We assume the oxygen-hydrogen correlation is done for bulk water. It's not done for every single solute atom in every configuration on the surface because you can't parameterize that. Yeah. So they have to. I'll come back to that question. I'll see if I can find that out by tomorrow. Oh. Other questions? I want to say a little bit about how these models do. So I don't have results for the Salsa model. The Salsa model is quite accurate. The Salsa model's main advantage is it really has a much better description of the cavity, and it also has it has fewer parameters than many of the other models, especially the quantum chemistry models. The comparisons I found. It was one in the literature which I wanted to show here. Here's a method in Gaussian. This is a finite difference Poisson-Boltzmann solver. It doesn't tell you anything by the name. I want to just say these two models have an enormous number of parameters in them. These models are parameters by the atomic radii for every single atom in the periodic table. They parameters by some partial charges for every single atom in the periodic table. They also then, of course, parameters by there's an epsilon in there, there's an interfacial energy term in there, and a couple other models. So these have an enormous number of parameters in them. VASPSOL has 3 parameters in it: the dielectric constant, 4, the tau, the interfacial energies, and then the function for forming the cavity, which has a width, and a critical density where it happens. And as you can see, you can do things with lots of parameters. Especially SMD and VASPSOL are in spirit actually quite similar. Lots of parameters, 4 parameters, and you get essentially the same accuracy. The FD PB is a little bit more accurate, has a lot more parameters in it, more carefully done. So in other words, most of these polarizable continuum models all do somewhat similar, right? So there's not a very dramatic difference, and fewer parameters is certainly something we like. I'll show you also where it fails. Here's another comparison. This is one we've actually done on the Minnesota solvation model. We looked here in this case at the 274 solvation Gibbs free energies in water. Right? And I'm going to come to the non-aqueous on the next slide. And then you see models like here the QChem model. There's that finite difference Poisson-Boltzmann solver again. There is a polarizable continuum model. That's actually very similar in spirit to what VASP-SOL does. And then there's the Cosmos and the Cosmo-RS model. Those are commercial models, heavily parameterized also again. And if you look at them, the heavily parameterized models, certainly on those systems, they've actually been optimized on the database. Some of these do very well, right? They have an error which is about half that of the other models. But then again, our 4-parameter VASP-SOL and many other solvation models, they do comparable. And it's a kilocal per mole. So for simple solvation energies, these are mostly neutral molecules. I think there's some charged ones in there as well. It does pretty all right. It's useful for that. Here's an example that's from our own work, and I want to say more of that in workshop 2, a lot of the technical details. We always thought, when we used the parameters, we essentially copied them from JDFTX, which was fit to 6 molecular solvation energies, a very small number of fitting data, but it also was only 4 parameters to fit. There wasn't a lot to fit. And we exactly copied the parameters from the first JDFTX implementation by the team I showed earlier, by Arias et al. And so what I'm showing here now is actually taking those original parameters and testing them on the whole Minnesota database. We test them on water. Those are the blue points here. And they actually fall pretty all right on the diagonal. It doesn't do too bad. Gets an R squared of 0.88, an MAE of 1.2 kilocal per mole, and MSE of 2.3 kilocal per mole. So one would say that has predictive power. We however identified also that a lot of users of our solvation models and the other solvation models were interested in all kinds of different solvents. And all they did is they changed the epsilon. It's like, okay, that's what I would have recommended them, right? I don't know any better. And when you look at that, if you just change the epsilon and leave the water model otherwise intact, you get an R squared of minus 4.4. So the answer to that, in other words, is much worse than just randomly guessing almost, right? So it's certainly not correlated. The MAE is 5 kilocal per mole, the MSE is 30 kilocal per mole. But if I would have just given them the average solvation energy in the database is, just use that number, that R squared would have at least been 0. And the MAE and MSE would have been probably a little smaller too. So in other words, that was a terrible choice. And so it bothered us. And so we actually re-optimized the VASP-SOL parameters somewhat. There's only 4 parameters, not a lot of 3 parameters. The epsilon you don't choose is given by, to make that cloud of red curves points a little better. One problem with optimizing solvation model parameters to those data sets is you have to do an awful lot of DFT-cation for all kinds of parameter choices and stuff like this. So we decided to use an AI model to actually simplify that, an active learning optimization, and we've got it to be a little better. We also decided we're trained on the Minnesota database, but then we had no testing database. Well, my student was actually funny. I trained on everything. What do I do now? Right? So, well, we've got to find an independent database, and we did. There is a solvation database at TU Munich, an independent data set. That one is actually based on experimental partition coefficients, chemical engineering lingo, to calculate those solvation energies. That's perfectly reasonable. And we tested on that one after optimizing it. So before optimizing it, now I'm only showing you the non-aqueous ones. The aqueous ones actually didn't make that much difference. The model was pretty good. But the non-aqueous ones, originally, that was a crazy cloud there. And you see here, we separated them in 2 categories. There is the ones which overlap with the Minnesota database. You actually at least have the solvents in there, even though the solutes were different. And then there's a non-overlapping set where the model knows nothing about those solvents, has never seen a solvent like this in training, and never seen the solute either in training. And so it does, of course, completely terrible. But when we optimize it, it does actually quite well with the overlapping solvent. The R squared is positive, that's a good sign. MAE and MSE is kind of sort of what you expect. And from the non-overlapping solvents it's never seen, the R squared is still negative, so it's still pretty terrible. But it's still a major improvement from incredibly terrible to slightly terrible, right? And so, there is some hope, is what I'm saying there. So what I would say based on that, in a 4-parameter model, you gotta have some solvents in your you gotta have the solvent in the training data if you want to know what its solvent behavior is. If you don't, you're really just doing a little better than random guessing, actually a little worse than guessing the average. Okay, so the AI can help you to improve these things even for non-overlapping solvents, but if you don't have any data, we've heard that in the previous talk, you're really grasping at straws. So some takeaways for implicit solvation models. So they capture the solvent effects quite efficiently. So the numerical efficiency is impressive for electrochemistry and catalysis. They replace the molecules with a completely smeared out continuum with potentially some correction terms. They're self-consistent, variational. They implement it in all major DFT codes. And for aqueous systems, I think they're pretty good. The limitations I mentioned is most of the models, JDFTX has gone beyond that, but most of the models are local, mean field approximation, static response. So they underestimate the solvent structure, they neglect the dynamics. And so there's clearly a lot we can do by applying machine learning to things, making the kernel nonlinear, just in the salsa method. And so the vision really for us is to kind of sort of implement these terms to really bring the DFT with the implicit solvation model to reproduce experimental results. I've mentioned already some of the assumptions and limitations here. And so if time permits me tonight to really get that put all together, I'm going to give you tomorrow a brief introduction of what classical DFT does for the description of the liquid and how we can try to put these concepts together. Thank you very much for your attention.